Let's spend a few minutes talking about the key features and behaviors of exponential functions. And for this one, I've chosen a function that has a bunch of transformations in it right here, right? We've got 2e to the negative x plus 3 minus 4. So we've got all sorts going on. There's a reflection, there's some shifts, there's a stretch. But I want to focus on what the key features are. Now, one of these should be very, very obvious, right? It's an exponential function, which means negative infinity to positive infinity, right? You should know that about any exponential curve, it has all the x values, and there's no domain restrictions. But in terms of the range, we do have some restrictions. And if you look at the picture, it's pretty obvious. We're looking at a horizontal asymptote right here. Okay, that's sitting there at y equals 4. The function will never, y equals negative 4. The function will never drop below y equals negative 4. And you can see where that comes from in this equation right here. That's just the shift at the end. That's the vertical shift. That's the effect on the horizontal asymptote. So my range is negative 4 to infinity, right? It includes all the values over that, but nothing under it. And not negative 4 itself either. That's a rounded parentheses. It's an exclusive inequality. Now, in terms of the intercepts, this is where things get a little more interesting, and we're going to have to use our experience with equations to solve these sorts of things. So for the x-intercept right here, what I want you to remember is how you find x-intercepts. You set y equal to 0. So that means 0 equals 2e to the negative x plus 3 minus 4. Now we're going to solve this equation. We add 4 to each side. We get 4 equals 2e to the negative x plus 3. We divide each side by 2. We get 2 equals e to the negative x plus 3. Well, that's as far as you can go with basic algebra. And now we need to start using properties of exponentials and logarithms. Remember, if you take the log of each side, in this case, I'm going to use the natural log because I'm dealing with the e, the Euler's number on the right. We get the following. Natural log of e to the negative x plus 3. All I did was I took the natural log of each side. But what's nice is the right side is going to cancel out very conveniently. This is why we choose natural log. I just get the following, negative x plus 3. And now it's easy to simplify this. I'm going to add x to each side, and I'm going to subtract natural log of 2 from each side. Now that is my x-intercept right there. So I would say it like this. That, comma 0. Okay, this is my x-intercept in coordinate form right there. Okay, so that's the form that you would be expected to enter the x-intercept in. The y-intercept, a little easier. We're going to do this one in orange. So the y-intercept, all you have to do is set x equal to 0. And I'll do that one down here where I've got some room. So setting x equal to 0, in other words, f of 0 equals 2e to the negative 0 plus 3 minus 4. Well, just simplify. That becomes 2e cubed minus 4. And that's as much as you need to say. You can just say, x equals 0, y equals 2e to the 3 minus 4. Now, what is this thing? Well, 2e to the 3 is something big. Let's see. For the curious among you, let's see, e cubed is about 20. So we're looking at 2 times that, 40 minus 4. We're looking at about 36.17 or something. But I don't want you to answer that because if you answer with decimals, you're going to get marked wrong in this problem. This wants you to give the exact answer. So 2e cubed minus 4 is the y coordinate of the intercept. And now we move into some things that really should be quick. Do you see any local maximums? No. Right? That's very obvious. It goes up forever. What might confuse people is the idea of a minimum. Whether it's local or absolute, in both cases, there is none. Okay, there is no absolute minimum because it's going to keep going down and down and down. And if you say the minimum's right here, well, I'll say, what about right here? If you say that one, I'll say, what about right here? See, it keeps getting closer, but never actually reaches negative 4. So you can't say negative 4 is the minimum either. It has no minimum. It gets awfully close to negative 4, but never reaches it. Now, in terms of increasing and decreasing, you can see this thing is never uphill. So there is no increasing interval. But decreasing, yeah, sure. All the numbers. Negative infinity to positive infinity. It's decreasing on all those x values. And then in terms of constant, it's not flat anywhere. It gets awfully close to flat, Don't mistake this for flat. It's not. It's just extremely shallow. And then in terms of positive and negative, this one is interesting. You have to look at that x-intercept that we found in here. Okay, right? That x-intercept location, what was that? 3 minus natural log of 2. So anywhere to the left of that, it's positive. And we have to find some way of saying that. The way you do that is interval notation, negative infinity, 2, and this looks a little weird, 3 minus natural log of 2. Okay, that's the point where it stops being positive. And then it starts being negative just after that point. So we'd say 3 minus natural log of 2. Okay, that's the x-coordinate. And out to infinity. And those values are all negative. Remember this 3 minus ln of 2? This thing right here, that is a number. We just don't use the decimal value. We use the exact value for it.